So, here we go. Problems 48, 49, and 50 in quick order. If f is continuous, decreasing function from 0 to 10, with a critical point at 4, 2, which of the following statements must be false? Okay, let me just draw this out, just so I can get an idea. It's continuous, it's decreasing, and it has a critical value at over 4 and up 2. So I'm imagining this function doing something like that. And here we are at 10. Right? Is it true that f of 10 must be the absolute minimum? Oh wait. Is it false that f of 10 is the absolute minimum? Well, it's decreasing. And we know that on every closed interval, there's got to be an absolute max and an absolute min. If the function's decreasing, it sure seems like this would have to be the absolute min. I can't see any argument. I don't think that's a false statement. I think that's an absolute true statement. Okay. I'm trying to read your faces. You guys are not reading really well right now. Okay, let's try another one. F of 4 is neither a relative maximum or a relative minimum. That's that point where we have a critical point there. We don't know. How can it be decreasing? How can it be decreasing? Well, I guess it could have a horizontal tangent and then fall like that. So the function is decreasing, but at that one point, it's a 0. The slope is a 0. I think it's true that there's neither a relative maximum or minimum. I think it's true because before the values have to be higher, and after the values got to be lower, and for it to be a relative minimum, it has to be the smallest on an interval, and the largest or maximum the largest on it. I think that is a true statement. So if it's a true statement, we're only looking for false statements. It's not our answer. Could it be that f prime of 4 does not exist? Well, I mean, it tells us there's a critical point there. Could this be like a piecewise linear function where there's a corner there? I mean, that's a really poorly. You can't see the corner there. Let me try that again. Whoa, where'd my axis go? All right. Could it be like function like this, where it's decreasing? That could happen. That could happen. So must it be false that it did happen? I can imagine that could be true.
The only one that you for sure know that it's not true is, like, all of them could be maybe, but E is definitely not true because then it wouldn't be a critical point.
Let's see. So the argument, Marley, let me go through the argument. It's a critical point, so it's either got to be undefined or 0. If it was defined and it was less than 0, it couldn't be 0. It can't be 0 and less than 0 at the same time. Or undefined. That is correct. That seems to me like the right reasoning. Okay. Can't be, if it's defined, if it's undefined, it can't be less than 0. And if it is defined, to be a critical point, it has to equal 0. All right, that's good. Oh, and it's the right answer. Now, who asked this question? Did we make it any better? We have a better definition. We have actually a better definition in not this lecture, but the 4.3 lecture. Okay. So we'll get a better definition of decreasing, and then you'll say, oh, okay. All right. So that's 48. How about 49? 49. Which of the following functions has exactly 2 local extrema in its domain? Well, let me tell you the ones I can eliminate. Based on my knowledge, it can't be D. The graph of the tangent function. The graph of the tangent function has no local extrema. Ever. Right? So it can't be tan. Okay? Now, what do I know about absolute value function? Corner. You think it's going to have local extrema? Well, if it does, only one. So that can't be it. All right. So now what do we have left? We have 2 cubic functions and that one.
That one's going to be all like, oh, it's going to be 1 over x.
Well, I'm just thinking about what I know about the graph of natural log x. Graph of y equals natural log x looks a lot like this. If you add x to every single value, does that, because natural log x is only defined for positive values of x. I don't see this having any local extrema, just from my knowledge of that graph. All right. Now, Marley, you want to attack this problem in terms of looking at critical values?
Well, because if I were to look at that, I wouldn't like off the top of my head know what x plus ln x looks like.
Okay.
But if I don't know, I can kind of figure out 1 plus 1 over x is more of a something I could see
Okay.
in my head, and that just it doesn't matter.
Can I ask a favor of all of you?
Sure.
Can you between now and let's say the next couple of days, can you refamiliarize yourself with what the graph of natural log x looks like? It'll be really helpful for some other stuff. But if we forgive it for now, add that on that list of things to do. All right. Here's the other way. Here's the other way to attack this. If you want to find out if there's 2 local extrema, that means there'd have to be at least 2 critical values. When I think the derivative of this function, the derivative of x is 1, the derivative of natural log x is 1 over x. If I give it a common denominator, it's undefined at 0. But you know what? That function isn't defined at 0. Natural log is not defined at 0. And when does the numerator equal to 0? When x is equal to -1, and this function is not defined at -1. So by knowing what the graph looks like, or by taking it for critical values, we know that there can't be 2 local extrema. So it can't be this one. Hey, we're down to those 2 polynomials. Now what? Should we do the same analysis here? Take the derivative, and the derivative for this one is 3x squared minus 6, and the one for this one is 3x squared plus 6. Now, I believe one of these 2 has no solutions. So if I took this 6 over to the other side, I get something squared is equal to a negative number. And that doesn't happen in the real number system. Okay. So it looks like this one ends up becoming x squared is equal to 6 over 3. X squared is 2, which means x is equal to plus or minus the square root of 2. And that would give us at least 2 critical values, which would give us the opportunity to have 2 of those 2. I think that's it. Oh, all that work to find out that it's B, and of course it says B right there. One more in this grouping. Are you ready? Woohoo!
Right.
50. see there's a difficulty with this problem because we don't know what even functions are. All right, so review time. A review of what we mean by even function. Now, I can do this review in two ways. I'll do it the easy way first. Even functions are functions that are made up of only even powers. So, for example, f of x is equal to x squared is an even function. F of x is equal to x to the fourth plus x squared is an even function. F of x is equal to 10x to the 8 minus 2x to the 4th plus x squared is an even function. And because x to the 0th, 0 is also an even number, I can add any constants onto here and they still remain even functions. That is me just giving a bunch of examples of even functions. That's item number 1. That's the easy stuff. Item number 2. Next level up. Even functions have symmetry about the y-axis. The second attribute. These are not contradictory definitions. They're just, the first one is a list of examples. It's incomplete. The second one is fine because if you see the graph of an even function, you can recognize it because you can think about doing that fold and getting that reflection. Okay? On to part 3. Part 3 is the actual definition. Even functions have this property. F of x is equal to f of negative x. Even functions have that property. Okay? Means that if I have the symmetry like with the parabola, and this is, let's say, the value 2, if the point 24 is on one side of the function, I can put a negative 2 in front of it and it's still going to have the same functional value. For every point on the right-hand side, there's another point with the opposite value for x that gives the same functional value. All right, so there we go. An even function with the domain of all real numbers has a local maximum at x equal a. So there's a local max. And that means that's the local max that goes down on either side of it, right? Or something like that. And what does this symmetry tell us? That over here, there's another point, negative f of a, and it's got things going down on either side of it as well. So what do we know about local f of negative a? That it also has to be a local max because, again, we have that symmetry. You good? Complete? Okay. Since we did a quick review of even functions, can we do a quick review of odd functions? We might as well put it on there. So, red for odd. Okay. So, what do you think are the examples of odd functions?
Odd powers.
Okay, the ones with odd powers, like x cubed, x to the first, or any combination thereof, right? 3x to the 5th minus x cubed, for example. Right? So there's your examples of odd functions. Are they symmetric? They are. They are symmetric about the origin. They have what's referred to as point symmetry, not line symmetry. Point symmetry, not line symmetry. The most sort of famous object that has point symmetry the yin yang. And what does that mean to have it that has point symmetry? There's a point, and for every point that's on the curve, I can draw a point through that center point and then equidistance along that line, and I'll line back up on that point. It has point symmetry. Cosine. I'm sorry, the sine curve, I'm sorry. The sine curve has point symmetry. It is considered an odd function. For every point I have here, I can go through the origin, and then same distance along that line, and I'm back on the curve. Which leads us to the last part of the definition. The true definition of a odd function is that f of x is equal to negative f of negative x. For every point that I have here, call it a, f of a, there's a point over here, negative a, and where this one was positive, the other one is negative. So these occasionally come up in discussions during calculus class. You should have those definitions at hand. All right. I had already announced that we were going to have a quiz today. All right. So